This weekend marked 45 years since Mount St. Helens erupted.
It was very stressful, exciting, but very stressful at that time.
So you were monitoring the mountain for the 2 months leading up to the eruption?
That's correct.
The explosion blew 1,300 feet off of the volcano's height, sending ash 80,000 feet into the air.
What if I told you that beneath the serene slopes of Mount St. Helens, America's most notorious volcano, there's a new kind of mystery brewing? Not ash, not lava, not a sudden explosion, but something quieter, still shrouded in scientific uncertainty. A small, unexplained surge of heat rising from deep within the caldera. One that has left researchers more puzzled than at any point in the decades since the 1980 cataclysm. 45 years have passed since Mount St. Helens shattered the calm of the Pacific Northwest, hurling ash across entire states and killing 57 people in moments. Scientists learned hard lessons that morning. They saw firsthand the power of a mountain that had, until then, been just another scenic landmark. The world pledged to keep a closer watch for the next warning signs. But what if the next signal from the mountain isn't smoke, or rumbling, or earthquakes? What if it's something far subtler, something that challenges our assumptions about how volcanoes speak to us? What if even the most seasoned volcanologists are left scratching their heads? Now, as Mount St. Helens' 45th eruptiversary arrives, a new question hovers over scientific gatherings and monitoring teams, usually masters at reading subtle cues, temperature shifts, gas emissions, minute tremors. Researchers are confronting new readings, a slight rise in the caldera's surface temperatures, the kind of signal that typically accompanies activity underground, yet arrives without the classic hints of an imminent eruption. Are these just echoes of the mountain's violent past? Or is Mount St. Helens reminding everyone that its story isn't finished and that some chapters are still unwritten? Beneath the ash, what 1980 taught us and what remains to learn. The story of Mount St. Helens has always begun and ended with transformation. On May 18, 1980, it went from an almost symmetrical peak, dubbed the Fuji of the West, to a battered amphitheater of broken stone. The north flank collapsed in the world's largest recorded landslide, unleashing a lateral blast that reduced 230 square miles of forest to wasteland in mere seconds. Rivers were rerouted, towns smothered in ash. A whole region was transformed overnight. Out of this unprecedented destruction, volcanology in the United States was profoundly changed. Scientists grew intensely focused on early warning cues, regular seismic rumbling, inflation of the ground, worrisome levels of volcanic gases, swelling of the volcano's surface as magma gathered beneath. They mapped out gas vents, measured every tremor, and cataloged all signs of restlessness. When, in the years that followed, Mount St. Helens continued to emit steam and minor earthquakes, when it started rebuilding its lava dome inside the crater, few were truly shocked. Such activity, they agreed, was within expectations. The volcano remained restless, but predictably so. As the forests began to recover and new monitoring systems took root, most scientists believed that by watching closely enough, they'd catch any early warning signs in time. But as years passed, another fact became clear. Not every eruption follows the textbook script, and when familiar signals fail to appear, caution grows. Recently, a different marker has prompted new debate. An unexplained pocket of warmth, quiet, lingering, and so small that it would be invisible to anyone not looking for it. It's not accompanied by new jets of gas, nor the familiar uptick in tremor, just a rise in temperature, steady, subtle, mysterious. Mount St. Helens, it seems, still reveals just enough to keep us questioning. A heat signature with no name. For generations, scientists have used powerful instruments to peer beneath the Cascade volcanoes, assembling pictures of vast molten reservoirs and intricate networks of faults. a fiery world unseen from above. Typically, most volcanoes signal their potential for unrest through both deep and shallow heat signatures, but Mount St. Helens has more recently been shown to break this pattern. A recent study highlighted how, unlike its volcanic neighbors, St. Helens has an unusually cool profile at depth, while nearby giants host clear evidence for large, persistently hot magma chambers. Mount St. Helens is, in some respects, an outlier. Beneath its visible scars, it appears to lack a significant deep heat engine. This sets the mountain apart and has confounded expectations about what drives its eruptions. That was the consensus until puzzling new readings appeared. In early 2025, during ongoing research and monitoring for the region's bird and bat populations, scientists made an unexpected observation. At some of the 67 bird monitoring sites and 10 bat sites surveyed between 2023 and 2024, supplementary environmental sensors picked up a gradually rising trend. Surface temperatures inside the caldera were slightly higher than anticipated. There were no obvious explosive signs, no plumes, no urgent warnings, just a lingering, incremental warmth focused near the site of the historic 1980 blast and debris avalanche. Satellite data confirmed the phenomenon. The new warmth was invisible to the casual visitor, but clear in infrared images from orbit. The particular locations where temperature rises were detected broadly corresponded to areas reshaped by the 1980 event, places where the land's memory is already deep. There were no fresh swarms of earthquakes or unusual gas signatures to explain it. The ground wasn't bulging upward, yet the warmth persisted, subtle but continuous. Is this just the last thermal pulse from the 1980 cataclysm, now bleeding off decades later? Or is this the first hint of a process not yet fully understood? When volcanoes break their own rules. Ask most volcanologists what to expect before an eruption, and you'll hear a familiar list. Long sequences of earthquakes. These are the well-studied signs that magma is marching toward the surface. But Mount St. Helens sometimes writes its own rules. The apparent localized warming at the caldera is strange precisely because it's occurring without those classic warning markers. There are no new bands of harmonic tremor, a sign that magma is forcing its way upward, nor evidence of underground pressure building up. Gas sensors aren't spiking the way they would if magma were degassing shallowly. The mountain's surface isn't lifting dramatically. Instead, the anomaly is quiet. The heat lingers, unaccompanied, and the data doesn't follow familiar patterns. It's significantly subtler than the activity in the months leading up to the 1980 eruption. Still, any deviation from established baselines draws attention, especially in a landscape forever changed by past surprise. For scientists, the temptation is to puzzle out a cause using what's already known, perhaps the lingering effect of heated groundwater moving through buried debris, or some new geothermal process thawing ancient ice. Or is there a new pocket of warming rock, previously undetected, starting to influence local temperatures? With the usual playbook offering few answers, caution is the only certainty. Hidden dangers in the blast zone. For many, Mount St. Helens is already history, a mountain that spent its fury 45 years ago, surrounded now by reborn forests and winding trails. But for the people living nearby, and for the researchers entrusted with monitoring it, the mountain remains a source of vigilance and humility. The 1980 disaster is remembered in part for its silent menace. Though there were warning signs, earthquakes, bulging ground, scientists evicting residents from zones of greatest danger, many still misjudged the precise nature of the threat. While the telltale vertical eruption was on the radar, the northward lateral blast that ultimately occurred was a nearly unimaginable twist, one that transformed not just the mountain, but the science, and taught an entire discipline the cost of assumptions. Today, the subtle temperature trend has reignited a familiar tension. Researchers are once again combing through decades of measurements, trying to decide if this is meaningful, and if so, what it might herald. Could it be meltwater trickling through remnants of the avalanche, interacting with long-buried rocks still holding some heat, localized chemical reactions, thawing out old deposits? Or could it suggest, even indirectly, that when a volcano like St. Helens surprises, it may do so in ways that aren't yet written in the literature? What scientists know is simple. The absence of expected warning signs does not always equal safety. Some chapters of a volcano story are written in a new language. The science of uncertainty. Every technological and structural safeguard installed at St. Helens since 1980 is built on patterns. Sensors measure what erupted mountains have done in the past. The hope is that with enough vigilance, a new disaster can be averted. But a new or unexplained signal, a heat anomaly, especially one that doesn't fit the known sequence, throws those plans into doubt. Imagine watching for tremors, gas swings, ground shifts, and finding none, only to observe quietly that the caldera is warming in ways not previously recorded. Anomalous heat by itself is difficult to parse. Natural variations exist, and the aftermath of the 1980 eruption left a chaotic pile of debris, ice, and fractured rock that still influences the landscape's energy balance. Thus, scientists debate the causes. Is this just groundwater interacting with warmer debris? Could seasonal factors or subtle long-term changes in the landscape be responsible? Or does the change hint at activity deep below, still invisible to standard monitoring tools? In community planning, there's little precedent for what to do about a volcano hinting at unrest solely through temperature readings rather than shaking ground or billowing steam. Discussions in scientific meetings have grown more nuanced. If a heat signal is truly decoupled from classic signs, if there's no gas, no seismicity, no inflation, what level of concern is appropriate? For now, planners and researchers remain alert, knowing that nature rarely operates on human timeline. If you found this insight fascinating, don't forget to like the video. Share your thoughts in the comments. What do you think the heat signal means? And subscribe for more deep dives into the world's most mysterious geological events. Whispers among the watchers. Beyond the confines of research labs, concern quietly spreads. Some see unease as a reflex, with the anniversary date stirring old fears. But for those who have lived with the volcano's legacy, or who spend seasons hiking, measuring, or restoring the landscape, a subtle anomaly in the caldera draws fresh attention. After decades of research, routine survey work at the bird and bat sites has become a cornerstone of regional scientific collaboration. In 2023 and 2024, researchers at these 77 designated sites gathered a wealth of diverse environmental data, mostly about the health of local wildlife, but also about surface conditions, air, and soil temperatures, and other physical parameters. So, when trends in temperature readings diverged slightly from expectations, scientists were among the first to notice. The increases were modest, not the kind that would be felt hiking the slope, but enough to appear statistically in time-stamped logs. As remote sensing satellites scanned Mount St. Helens from space, the same signal emerged. The surface in certain caldera regions was persistently warmer than historical averages. The findings spurred conversation. Was this a new phenomenon, merely a temporary fluctuation, or something more persistent? Teams pored over old maps and logs, re-examining the 1980 debris field and searching for any precedent in decades of baseline data. This is not the first time St. Helens has challenged observer expectations. Many who survived the original blast recall how swiftly fate changed, how quickly morning routine gave way to chaos. Their message remains the same: take nothing for granted. The long shadow of 1980. Every meter of the blast zone tells the story of 1980, the landslides, the instant receipt of new rivers, and the reassembly of a shattered ecosystem are visible in every fallen log and exposed hillside. It began with a sudden collapse and ended with a transformed world, one whose recovery and recurrence remain topics of endless fascination and study. Year after year, as science and local memory intertwine, the lesson of unpredictability resonates. No eruption is ever identical. The mountain's future is carved by processes sometimes beyond human comprehension. The localized warming now seen in the caldera is far less dramatic than anything observed in 1980, but its very novelty draws attention. Researchers, both seasoned and new, speculate, is this a fleeting echo of old heat or the first line in a new pattern? For now, the heat is a question mark, one that makes everyone wary of overconfidence. The uncertainties are vast. If the anomaly is benign, caused by groundwater, by lingering heat in the debris, or by the land's slow, natural recovery, then it will dissipate, and careful study will explain it in time. But if it is symptomatic of deeper unrest, it demands vigilance and humility from everyone involved. The time bomb beneath the crater? After 1980, Mount St. Helens became the best monitored volcano in the country. Dense networks of seismic sensors, gas detectors, and permanent cameras crisscross the ground, connecting scientists in real time to any changes beneath the surface. Yet even with these tools, much remains unknown. The avalanche and eruption buried the caldera under a jumbled mix of ice, broken rock, and newly stratified deposits, the geological equivalent of a complex, living scar. Groundwater now twists through these deposits, interacting with unconsolidated layers. Local heating or thawing could indicate natural cycle, or, in more unusual cases, interactions with pockets of once-lost warmth. As researchers study the evolving thermal image of Mount St. Helens, they know how difficult interpretation can be. Even the most advanced remote sensing can be clouded by debris and chaotic subsurface arrangements. Instruments pick up changes, but the cause may remain elusive for years. For now, the mild heat anomaly has presented itself as a riddle, a subtle, slowly shifting pattern, lacking the drama, but possessing the intrigue to command attention. Lost in the data. Today's volcanology is highly quantitative. Most signals, be it heat, seismicity, or gas, are interpreted as departures from baseline data. The pattern that is emerging at Mount St. Helens may be hard to discern for any single observer, but when hundreds of measurements stack up, the anomaly becomes unmistakable. Each week, as researchers continue wildlife and environmental monitoring for the 2025 program, the temperature data is logged, reviewed, and compared to years past. Algorithms scan for patterns, outliers are noted and flagged. What appears is a signal, higher temperatures than previous seasons, holding steady across time. Deep thermal imaging, paired with satellite observation, confirms that the so-called cold core below St. Helens, a region previously considered less thermally active than analogs, has shifted. The change is not dramatic to the casual observer, nor is it suggestive of imminent catastrophe. But in science, small deviations can become the first clue in a much larger process. Why here? Why now? 45 years after the disaster that changed North American volcanology, what is Mount St. Helens? Helens communicating with this subtle warmth. Living in the shadow, a community on edge. For those who came of age after 1980, the blast is legend, a story told at museums, in science classes, and at reunions in the small towns that ring the mountain's flanks. But for others who remember the noon-dark sky, the loss of homes and friends, or the long weeks of ash cleanup, the memory is sharp, layered with caution. When news of an unexplained heat anomaly enters local conversation, even without talk of eruption, people listen differently. Drills are reviewed, plans are updated. Officials keep watch, knowing any significant change at the volcano justifies a higher state of readiness. The landscape, though regrown and partially healed, remains dynamic. Landslides, mud flows, and other natural hazards persist well beyond the memory of the last eruption. A slight rise in temperature, though not immediately alarming, becomes part of a catalog of watched signals, especially given the unpredictability of complex volcanic systems. Everyone understands the simple truth: volcanoes are never truly at rest. The echoes of their past power resonate in each new anomaly. Between the lines of nature's code. In the end, What Mount St. Helens may be telling us remains unclear. Is the subtle increase in caldera heat a fleeting artifact of natural processes, harmless and soon to subside? Or is it a small clue, an early sign that the mountain has more surprises hidden beneath its surface? Science, by nature, thrives on such mysteries. A new anomaly is rarely an omen, but always an invitation to investigate more deeply, to question old assumptions, to prepare for all possibilities. Mount St. Helens has already redefined what American volcanoes can do. Researchers remain cautious, always alert for new chapters. As monitoring continues into 2025, across dozens of wildlife sites and with new technological tools, scientists, planners, and the public remain attentive not just for rumbling earthquakes or columns of steam, but for the quieter signals, a warmth where there should be none, a pattern waiting for explanation. The certainty is this: the story of Mount St. Helens is not finished. Whether the mountain will speak loudly again or merely remind us of the depths of our ignorance remains unknown. For now, the caldera is quiet, its message delivered not in earthquakes or ash, but in a question lingering beneath the surface. Sometimes, the most important signal is the one we struggle the longest to understand. If this story intrigued you, be sure to hit that like button. What's your take on Mount St. Helens' silent signals? Let us know in the comments. Subscribe to stay updated on the mysteries shaping our planet. New insights are always on the horizon.